Hello, my name is Selim Engin, and I'll be presenting active target localization using noisy relative measurements. This is joint work with my advisor Volkan in the Robotic Sensor Networks Lab at the University of Minnesota. As an overview, I'm going to first summarize the problem of active target localization, the setting we study in this paper. I'll then describe some of the previous work conducted in our lab as background for our problem. I'll present our method for active localization, and we'll see how our method compares against the baseline approaches used in practice. Finally, I'll mention some of our ongoing work for extending the setting considered in this paper. Our motivation for this problem is to localize colored animals in the wild. Two primary methods for localizing animals use either colors with GPS or radio signals. The accuracy of GPS is usually much better, and it typically has an error of up to only 1 or 2 meters. However, since they consume a lot of battery power, the biologists would need to frequently replace the batteries, which is not really desirable as it requires loss of interference with wildlife. Therefore, we see the radio signal-based localization much more common in practice since it has better battery lifetime. The radio signals are usually quite noisy, and we need to get measurements from multiple locations to be able to triangulate the target well. In our previous work, we used aerial vehicles to localize animals, since they can cover long distances over short periods of time, and they can be used in various types of natural environments. Our multi-UAV system for tracking wildlife consisted of a group of 3 UAVs, each carrying a 3-element Yagi antenna and onboard processing units. The color we used on animals transmits very high frequency radio signals, and our UAVs are able to receive these signals. We conducted a series of experiments in an ecosystem science reserve where we deployed a single static target. In these experiments, we were given a candidate area for the target location, shown in a yellow square, and we were pre-computing the measurement locations for each UAV offline. We were able to report an error of about 7.5 meters in an area of 150 by 100 meters square for our estimations. So this is all good and well, but then we asked the question, what happens if we need to localize multiple targets with a single robot in an adaptive manner? To formally describe our problem, we are given a robot P equipped with a sensor obtaining noisy relative measurements. We are given a set of targets Q1 to Qm whose locations are unknown. And in this paper, we assume that we don't have the correspondence problem, meaning that each target transmits a unique signal. Finally, we have a function u that measures the uncertainty of the estimations given a measurement model. In essence, this function tells us how good the sensor geometry is for localizing the target position. And given all these, our goal is to find a path P such that the function u is minimized. In this paper, we focus on two different measurement models, bearing and range measurements. In bearing measurements, the robot at pxpy obtains a directionality observation measured from the positive x-axis. The measurement phi hat is modeled as the true angle phi plus some Gaussian noise. In our experiments, this noise can be up to 30 degrees. In the case of range measurement model, the sensor obtains distance observations, and the measurement is the true distance plus some noise. Since we don't have any directionality, the potential areas for the target look more like this hollow disk. In previous work, we have some methods that assume the target positions are known, or there is a good initial estimate for the target locations. These methods typically use some information-based strategy, such as a Fischer or mutual information. A more practical approach would be to remove this constraint. And commonly, we see methods that use some form of the greedy algorithm, minimizing the entropy over a region. There are multiple ways to measure the uncertainty of the measurements. We can use what's called a Bayesian histogram, in which each spatial bin corresponds to the probability of that bin containing the target position. For bearing measurements, these would look like these cones, since we only have directionality. And for range measurements, these look like disks, since we only have distance information. We can use the Bayesian update rule to update the histograms with each new measurement. As we can see in this figure, by taking new measurements, the localization uncertainty in the Bayesian histogram reduces. Another way to measure the uncertainty is by Fischer information. Fischer information tells us the amount of information an observable parameter carries about an unobservable one. In our case, we would like to measure how good the relative measurements are for locating the position of the target. We know that the determinant of the Fischer information matrix is inversely proportional with uncertainty. Therefore, we would like to maximize this expression shown here. Therefore, to maximize this determinant, we would like to minimize the denominator by being as close as possible to the target, or by maximizing the numerator. So the maximizing the numerator is when the difference in the angles phi I and phi j are close as possible to 90 degrees or to 70 degrees, which make the sign 1. And we sum this term over all pairs of sensor locations to compute the determinant of the Fischer information. One caveat is that this expression needs to know the true location of the target, denoted by Q star, which may not be always available to us. Our approach formulates the problem as a partially observable Markov decision process, or POMDP, and uses a reinforcement learning algorithm to compute its actions. In a nutshell, in reinforcement learning, we have an agent interacting in an environment where it receives observations and rewards corresponding to the states and actions it performs. The goal of the agent is to maximize the rewards it receives from the environment. We can directly use the noisy measurements phi hat as observations to our agent. Alternatively, we can compute the Bayesian heat maps and accumulate them to generate an image I sub t that can be used as input to our agent. We use a convolutional neural network called ResNet to process this image to compute the actions. Let's have a look at the reward functions we use for training our algorithms. For raw measurements, at each time step, we compute the predictions for each target position, and we use the negative mean squared error as the reward for that time step. For image representation, we simply use the negative mean of the image and intensities. Since if the target is static, we would like to minimize the white pixels in the image corresponding to uncertainty over the environment. In our experiments, we compared our method against two methods, the offline Fischer and local greedy methods. The offline Fischer has access to the true positions of the targets and uses the Fischer determinant to select its actions. The local greedy, on the other hand, does not have access to the true locations like our method and uses a greedy selection methods for entropy minimization using the Bayesian histograms. To briefly go over our results, we see that the offline Fischer is the best method since it has access to these true locations. However, our method is competitive as well. The plots report the localization error using the Bayesian histogram to over 50 time steps averaged over 100 different test episodes. In the table, we report the localization errors from the end of the episodes. We find that using the image representation is slightly better than using the raw measurements for the bearing measurement model. However, for range measurements, using raw observations is usually better. Here are a few snapshots of our method in execution. At each time step, we have these top-down images from the environment, which the agent uses to complete its actions. We see that the robot is able to localize the targets well from the measurement locations it chooses. And here is another example of the method in action. The red squares indicate the trajectory of the robot, and blue yellow dots show the true and predicted locations of the targets, respectively. These videos show the localization of 8 targets using bearing or range measurements. And although there are some failure cases which require taking multiple measurements from the same position, the resulting trajectories are usually successful. To conclude, in this paper, we investigated the problem of actively localizing multiple targets. We introduced the image representation for estimating the uncertainty in the measurements and used it as an input to our method. We also showed that our method performs well compared to the baseline approaches used commonly in practice. Our future work includes studying the case where the targets move, potentially adversarially, and we would also like to work on exploring coordination strategies among multiple tracking robots. As an ongoing project, we are working on the pursuit evasion problem, where the target adversarially escapes from the robot. Here, instead of using relative measurements, the robot receives position measurements. However, there are visibility constraints, meaning that the robot needs to search the target when the visibility is occluded by the walls in the polygon. And with that, I just want to thank you for your interest in our work. You can find more information at this link. And please feel free to reach out if you'd like to discuss anything further. Stay safe and stay healthy.